professors and scholars, welcome. I am Xinjia from the University of Electronic Science and Technology of China. I am honored to share our latest research on stacked intelligent metasurface enabled near-field multi-user beamfocusing in the wave domain, where stacked intelligent metasurface, or SIM, is integrated into the base station to enhance the near-field communications. Following my introduction, I would like to guide you through our study. Today's report is structured into 5 sections: background, system module, problem formulation and solver, simulation results, and conclusions. Let's first discuss the background of our research. Generally speaking, a SIM comprises multiple programmable derivative metasurfaces, each containing numerous low-cost mid-atoms. This multi-layer structure allows the SIM to emulate a physical neural network, effectively manipulating electromagnetic wave behavior in the wave domain, specifically by appropriately configuring the electromagnetic response of these meta-atoms. SIM can perform advanced signal processing and computing tasks required in wireless communication applications, such as MIMO pre-coding, benefiting from the advanced wave-based computing program. SIM has the advantages of ultra-high parallel computational efficiency, simplified hardware architecture, and extremely low energy consumption. The exciting works have been verified that SIM has ability to perform near-field beamforming in the wave domain. However, the following features limited the system performance. Specifically, feature A: the current module's preliminary focus on far field. The corresponding channel is modeled based on planar wavefronts, which fails to leverage the large aperture of SIM arrays in the near field. Feature B: the modules assume an ideal amplitude response of 1 for the SIM meta-atoms, which does not align with the actual channel behavior and leads to mismatches in practical scenarios. To address these issues, this work demonstrates that SIM can replace traditional digital pre-coding to perform beamfocusing in the wave domain, while considering the proprised spherical wavefront and mid-atom diffraction behavior. Next, we delve into the system module. As shown in Figure 2, we considered a SIM-aided multi-user MISO near-field communication system, where the SIM is fabricated by L programmable metasurface layers, and each metasurface have M meta-atoms. Additionally, SIM is integrated into the base station with S atoms to serve single atom users, satisfying S equal K. Next, we model the direction behavior of the M's meta-atom based on its circuit module. Specifically, we determine the impedance of the M's meta-atom and calculate its transmission coefficient. Moreover, we derive the amplitude phase coupling module to understanding its direction behavior. Thus, the response of the SIM to the propagated electromagnetic waves can be obtained. Moreover, we model the near-field channel from the SIM to the user based on the spherical wavefront and subsequently derive the end-to-end channel from the base station to the user. Then we calculate the received signal and the SINR at the trace user, which allows us to evaluate the system sum rate at the downlink computation. Following this, we delve into the problem formulation and solvers. In this work, we aim to optimize the SIM coefficients and the transmitting power vector to maximize the system sum rate. However, given the deep coupling between these variables, we reformulated the problem as optimizing the SIM coefficients so that the NMSE between the SIM-assisted systems end-to-end channel matrix and from the base station to the user and that of a fully digital ZF is minimized. This approach allows us to decouple the two variables effectively. Next, we delve into the simulation results. As shown in Figure 3, we evaluate the impact of the far-field and near-field channel modeling on the SIM-aided multi-user MISO system, where we consider the normalized channel gain. Specifically, Figure 3 demonstrates that the system rate of the near-field channel modeling is 7.6% higher than that of the far field with 150 meters. This is due to the fact that the near-field module takes into account both the distance and the angle for the spherical wavefront channel modeling. As a result, the channel matrix having a higher rate results in a higher sum rate. Moreover, under all setups, the SIM relying on computation in wave domain approaches the ZF precoding performance. Figure 4a evaluates the system rate sum rate versus the number of users. Note that the performance of the throughput scheme gradually decreases due to the fact that the throughput-based solution results in the non-ignorable inter-user interference, which becomes survey as the number of users increases. By contrast, the proposed algorithm effectively utilizes the multi-user multiplexing gain for a small number of users, and it may result in a diminished capacity as the number of users increase beyond a certain value. However, the performance of the proposed scheme can be improved by gradually increasing the number of Metasurface layers. Figure 4b portrays the fitting NMSE versus the number of users, where NMSE of all streams decreases as the number of users increases. Note that a reduction in NMSE is obtained as the number of Metasurface layers increases, which revolves a fundamental trade-off between the hardware complexity and fitting NMSE. Next, we evaluate the system sum rate versus the number of Metasurface layers. As shown in Figure 5a, the proposed algorithm achieves 239% higher sum rate than the throughput scheme at 11 Metasurface layers. Figure 5b portrays the fitting NMSE versus the number of Metasurface layers. By contrast, The fitting MC of the proposed algorithm decreases as the number of Metasurface layers increase. Specifically, NMC decreases from 0.74 to 0.002 as the number of Metasurface layers increase from 1 to 12, which implies that multi-layer SIM has the ability to effectively tune incident electromagnetic waves and suppress the inter-user interference in the wave domain. To verify the ability of the SIM beamfocusing to suppress inter-user interference, we visualize the wave-based beamfocusing for the SIM-aided multi-user MISO near-field communication system. Specifically, the single-layer Metasurface can only focus roughly on 2 users due to its limited tunability capability for the incident wave signal. The SIM can roughly focus energy on all users at double-layer SIM. Furthermore, increasing the number of layers to 4, it achieves comparable focusing performance with the fully digital ZF stream, benefiting from interference cancellation capability brought by multi-layer SIM. Although the proposed algorithm for wave-based beamfocusing is a suboptimal solution, leading to minor energy leakage. To conclude, let's summarize the key contributions of our research. First, we proposed a wave-based beamfocusing scheme for SIM-aided multi-user MISO near-field communication systems. Second, we considered the direction behavior of the SIM atom. Finally, extensive simulation results verified that the effectiveness of the wave-based beamfocusing can close to the full digital ZF stream. Thanks for your listening. My presentation is over. Please feel free to give me your feedback and suggestions by email.